Welcome, Mindsetters, to this great 12 session doing maths. Guys, I hope you're ready. I'm excited. We're going to be doing a lot of work and a lot of good, hard work to get you guys nice and ready for your exams. And I've got Jacques here who's going to actually be telling us what's happening today.
So today we're going to do some interesting calculus. You've done some of the first principle stuff, so I'm going to wrap that up quickly. Then after that, we're going to look at differentiating polynomials or functions by using the rules of derivatives. Yes, folks, I'm going to liberate you from that very long method where you use the limit. And then finally, we're going to end the show off with some equations to of tangents to curves.
All right, awesome. So guys, you know the drill. While Jacques makes his way across the board, guys, holla at me. Speak to me on the page, www.facebook.com/learnextra. Guys, make sure you get chatting to me. Let me know what you guys are thinking. If you're lost anywhere, you need help, please do not be afraid. Just speak to me. If I help you to help yourself, you pass the exam. It's simple math. Get it? Haha, made a math joke. Anyway, so guys, I'm going to hand over to Jacques. Jacques, take it away.
Before I start, I've got a better math joke than him, folks. Great mathematicians never die. They just tend to infinity. Now, you've heard about that. When you were doing the first principle rules, finding derivatives by first principles, you saw the limit where h is approaching 0. That is what you were using, okay, to find the derivative of a function. Now, I just quickly want to recap this with you. Here's your cubic function. F of x is equal to x cubed. Now remember your definition. If you need to find the derivative with respect to x, you need to take the limit when h approaches 0 of f of x plus h minus f of x, all of this divided by h. Now, folks, this took the ancient mathematicians, I'm talking thousands of years ago, okay, that took them 2,000 years to perfect this idea, which became the most powerful idea in mathematics, and that is the derivative. Okay, and that's what we're focusing on today. So I hope you've got your pen, your paper ready, and that you're going to communicate with us on Facebook. So let's see what you think about this work. Okay, folks, let's see. We're working, first of all, with a fraction. And there's double trouble here. When you get this type of question in an exam, you've got to be very careful, because there is a fraction in here, and then in the middle of that fraction, you're subtracting things from one another. Okay, so let me just quickly go through the one that you've already looked at. We've got f of x is equal to x cubed. So what's the first thing we know? We know f of x is x cubed. What do we want to know? We want to know what is f of x plus h. Now on the graph, this is what's happening. You're at a point x. Okay, here I am, I'm x. Now I'm moving h units away from where I am. So the length of my arm will be h, and then I'll be at a new position, x plus this h. And that's physically what you're doing when you calculate f of x plus h. And in simple mathematical language, that means that x becomes x plus h all to the power of 3, folks. Okay, so there we go. We've got f of x plus h on the screen already. There it is. And what must I do? I must subtract f of x from it. So I'm subtracting x cubed from that. And what is left now? And this is the important point, folks. I'm just reminding you of things that you most probably already know. Okay? At this point, this is where you check yourself. Look at this. Every single term in the top has got an h in it. And that h at the top must get rid of the h in the bottom, which is going to approach 0. That was the big problem. Okay, and that is that denominator is going to become naught. Okay, folks, so you check yourself. You have got no reason not to get full marks for this question. You check yourself in the exam. Every term after you have subtracted must have an h in it. We remove the h and look at the beauty here. Absolute poetry. They cancel one another out, and I've got 3x squared plus 3x plus h, and now h can become 0. Okay, now that is why from this point here to that step over there, you make those h's naught. Okay, so that is going to, let me just use another color. This is going to disappear because that term is going to become naught. This term is going to become naught. And what am I left with? I'm left with 3x squared over 1 as an answer. Now, folks, this type of question in the exam, anything from 4 to 6 marks. Now, remember what I said to you. We're going to quickly look at another one as well, just to refresh your memory. What did I say? Watch out for that negative. This negative in the definition here is where you're going to make a mistake. Okay, that's the first thing. So if you substitute, and you heard Yuval saying that to the grade 11s now, if you get into the habit of when you substitute in mathematics, you use a bracket, then you will never fall into that trap. Okay, folks, so here, that's your first catch, was that negative over there. Okay, the second thing is to check yourself in this step. Once you've subtracted f of x plus h and f of x from one another, every term that's left must have an h in it. Why is that so? Because I must remove that h as a common factor to get rid of the h that lies in the denominator, because it's that h that's creating the problem. One last thing here, folks. Because this question is really straightforward and easy, we are going to mark you down on notation. Very, very, very silly to throw marks away on notation. Now, by that I mean, folks, look at this. We don't say here that the limit, this is the big thing that you guys do in an exam. You say the limit when h approaches 0 is equal to f of x plus h minus f of x over h, whatever, or the limit is equal to whatever is on this side. It doesn't really matter what I put there. But this thing there, it doesn't belong there. It belongs in front of the limit. It's not the limit when h approach that's equal to something, okay? You are calculating a gradient. That thing there is the average gradient between 2 points on a curve. Okay, how far are those points apart from one another? They're h units apart from one another. So what is the definition saying? The definition is saying to find the derivative, you need to take the limit when h approaches naught of the average gradient. It's not the limit when h approaches 0 is equal to the gradient. Okay, so please, folks, that's a serious notation problem. The moment you let the h's equal 0, you can drop the idea of the limit, because what did you do? You took the h's and you made them 0. Okay, folks, please, those are a few pointers for you when you do your exam question. Let's look at another one that is rather tricky, and that is the one where the x is in the denominator. Okay, the previous one, what made it a bit difficult was that x had a power of 3. Here, I've got 1 over x. Now, to remind you, I'll tell you how I always do this, folks. I always avoid the fraction. Whatever I try and do, I avoid the fraction. In fact, I call it the F word of mathematics, fraction. Okay, so don't ever forget that. If you see a fraction, you want to get rid of it in the best way that you can. Now look at this. This is a fraction. I don't like fractions. So here, look at what's going to happen if I apply my definition, folks. You sit with what we refer to in maths as a complex fraction. That is a fraction on top of another fraction. And look at how ugly it becomes in the following step. The first time the fraction looks a bit better is in the third step. Okay, so be careful of those. What I tell my students to do is I say, you know what, apply the definition. You've got f of x. So now go and calculate f of x plus h. It is 1 over x plus h. And then look at what I do next. I work out the difference between the y values. I'm not going to divide by h yet. Okay, because I'll show you now why, folks. And the only reason why I do is because I see how many silly mistakes we make if we're under exam stress. Okay, so what do? I say this is nothing other than 1 over x plus h minus 1 over x. Now there I have my LCD. I'm subtracting two fractions. So this becomes an LCD of x multiplied by x plus h. And I have x minus, now remember the minus, I warned you, okay? Put a bracket down immediately, because this is x plus h. If I forgot the bracket, that would have been x minus x plus h. Big mistake, big mistake. Okay, now look at the poetry here, folks. If I now go one step lower than that, I can clean this up. X minus x is nothing. I've got minus h over x, x plus h, which is exactly what we have over there, but without the h's. Okay, so what did I do? I dealt with the fraction separately. I first worked out the top, the numerator here. Now I'm going to bring in the denominator. Now I'm going to say, okay, I know one thing. And that is that if I divide by 2, it's the same as multiplying by 1 over 2. Okay, or if I divide by a third, it is the same as multiplying by 3, the reciprocal of it. Okay, so here I'm going to divide by h, yes. Okay, so instead of dividing, I'm just going to say, okay, I'm going to multiply that with 1 over h. Look at how lazy I am now. All I do is I put brackets around what I've done so far. I've got 1 over h. The h's say goodbye, and I've got minus 1 over x multiplied by x plus h. Okay, so that therefore has been, is my gradient. My average gradient between the points x plus h and x. I must still take the limit. To make it a derivative, I need to take the limit. Now you know this, I'm just reminding you about it again. Okay, so my definition, the first derivative with respect to x, that's what we call that. The first derivative with respect to x is nothing other than the limit when h approached 0 of f of x plus h minus f of x all over h. That looks like an n, it's actually an h. There we go. Great. Okay, folks, so that's my definition. It's the limit when h approaches 0 of the average gradient. Okay, that is nothing other than the limit when h approaches 0 of minus 1 over x times x plus h. And again, we have a situation now that I can drop this because I'm now going to make h 0. Okay, and I'm left with minus 1 over x times x, which is x squared, which is indeed what you saw over there. Okay, so I just find if you're scared of fractions, the fraction that this generates, folks, it's rather ugly. It's called a complex fraction. It's a fraction on top of a fraction. They're not nice to work with. Okay, so I'm trying to avoid it by breaking the definition up bit by bit. I first worked out the difference in y, found an answer, then I multiplied by 1 over h. Why can I do that? Because I know that if I divide by 2, it's the same as timesing with 1 over 2. Okay, so I'm using the fraction principles here to my advantage to avoid the ugliness that I can be working with. Okay, let's move on. When you find the gradient of a function by first principles, you've done quite a few of them up to now, and what I've got on the board is I have a few of those results that you came across. If f of x was b, now remember this b here is a number, it's a constant, it's some constant. Okay, it could also just be a b. But I want to differentiate that. I see, but hang on, the answer was naught. So if this was 4, if f of x was 4, its derivative would be 0. Okay, if f of x was x, its derivative, first derivative with respect to x, was 1. When f of x was 2, its first derivative with respect to x became 2x. Okay, and we can continue. We saw x cubed again today. The first derivative, we have x cubed as f of x. Its first derivative became 3x to the power of 2. And the last one that we saw was 1 over x, which, by the way, we can write in exponential form as x to the power of negative 1. Now, if we differentiate that, it became minus x to the power of negative 2. Folks, there's something happening here. There's a pattern that you can observe. Now, let's try and see what that pattern is. If I look at x squared, or let's start at x squared. There was a 2 in the power. That 2 is now in the front of the x. The old power for the x was 2. The new power for the x is 1. That x has a power of 1. Now let's see if that is true. Is the power dropping down and is to become a coefficient? And is that power dropping by 1 all the time? Let's go to x to the power of 3. Well, if that is the case, here, if x to the power 3, if I differentiate it and the power comes down, then I'll sit with 3x to the power of 2. And that is indeed what we saw when we calculated its derivative. Okay, now let's look at x to the minus 1. The power x minus 1 was f of x. The derivative, or f prime we sometimes call that, should then be the power comes down and the new power is the old power reduced by 1, which should make it minus x to the power of negative 2 over here. Okay, now I conveniently started at x squared. What about the x? And what about the first number? Well, let's have a look. If I work with x, my power for x is 1. Okay? So if I go from x to the derivative of this x, that 1 comes down. It becomes a coefficient of the x. The x is still there and the old power is still there. But to find the new power, I need to reduce that old power by 1. Now, folks, look at the poetry there. If I clean this up a little bit, I get 1x to the 0. And we all know that if I raise something to a power of 0, something other than 0, okay, to the power of naught, I get an answer of 1. So this will give me 1 times 1, and my derivative will therefore indeed be 1. Now, what if there was a 4 in front of the x? Let's change it quickly. This was a 4x. Let's see what happens then. Okay, the existing coefficient is 4 over there. What happens is that 1 that was the old power comes down, multiplies with the existing coefficient. So it is still 4. So over here I have 4, x to the power of naught. So my result will be 4 over there. Okay, so if I have an x by itself, the derivative is the coefficient of that x. If I have 3x squared, folks, 3x squared, not just the x squared, a 3x squared. I'm going to just extend my page a little bit to get there. I have 3x squared. This is my function. There's my derivative. I've got 3x squared as my function. If I now want to find its derivative, the rule that we're seeing coming up here is the existing coefficient multiplies with the existing power. So the power comes down and it becomes a coefficient. The x to the power 2 remains, but that old power reduces by 1 to give us the new power. So with an existing coefficient there, this becomes 6x to the power of 1. So the function was 3x squared, and its derivative was 6x to the power of 1. Now, quick one here. 2 comes down, multiplies with a 3 to give you a 6. The 2 is still there. You take 1 away from the 2, you have a result of 1. So what happens to every single function that we differentiate? The powers become coefficients, and the powers reduce by 1. Folks, now that's a lot to take in. I know that's a lot to take in, and we're going to look at the constant, and then I'm going to talk to Ty about what you guys are saying to me on Facebook. Okay, let's do a quick 6. There's nothing with it. There's no x. So what's that x? X is 0. Okay, folks, after this ad break, we're going to talk to you, and we're going to see what happens to that. Okay.
So guys, I hope you've been paying attention. I hope that you guys have been writing your notes like I always tell you to do. You guys have been paying attention. And guys, you know I still have these to give away. So keep posting, keep posting, keep posting. Maybe you might have one of these coming to you soon. But for now, guys, I also want to send a quick shout out to Liberty. Thanks for sponsoring the show. For now, we'll see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. You had a nice little chill. You know, just put your brain on ease for a little bit. But now I need you to switch your brains back on because we need to get straight back into this. And guys, keep chatting to me on the page. Keep sending me your questions. If you're lost anywhere, if you have any great suggestions, if you just want to chat and just say, hey, I'm on the page, do it. But for now, guys, I'm going to hand you straight back to Jacques. Jacques, take it away.
Great. Thanks, Ty. Folks, as you saw, what happens is this rule over here. Let's take it and let's see how we can talk about it. This is any function. I want to differentiate with respect to x. Now this d dx, by the way, look at this. If I say to you f of x is equal to x to the power n, okay, then the first derivative with respect to x. That's what that says. It says it's the first derivative with respect to x. It means I'm taking this function and I'm differentiating it once with respect to the variable x. Now what did we say? The power comes down, it multiplies with the existing coefficient, which by the way is 1. Okay, x to the power of n, there's the n, and that's the old power, and what happens? The old power reduces by 1. Now, what you see here in the the white box here is something that looks very different. Okay, it looks particularly different from the f prime x that I've written down there. The only thing that it's saying, it's a different notation. That's all it is. It is still saying differentiate whatever is over here with respect to x. Okay? So there's more than one way. That's what I'm trying to say to you. Now you know that y is f of x. It's the same as a y value. So I can say that I'm differentiating by indicating it with f prime x. Or I can say I'm going to dx that y. In other words, whatever is written on this side, I'm going to differentiate with respect to x. One last way that we also use, this is just the notation I'm talking about, okay, is to say we use a capital D with a small x there. We use the square bracket. If I can just get my pen here, there we go. We use the square bracket and we put the y into it. Now we don't need to put that y into it. I mean, if y was equal to 2x, then this will be the d dx of 2x. And this will be the dx of 2x. Okay, folks, it's saying differentiate with respect to x. How many times? Once. Okay, so all three of these, all three of them, that, this, d dx, and capital dx, all of them are saying the same thing. Okay, so if we look at this, what is on this board as a rule now? We've got the d dx of x to the power n. What happened? That n in the power came down, became a coefficient. There it is. The old power was still x to the n, and what happened? I reduced it by 1. Okay, so let's do a few of them. We want to find the d dx of 5x squared plus 4x minus 1. A quickie. Okay, what do? Look at the notation. Look at the notation. I'm going to say it again. Look at my notation. I use it differently to when I used f prime. Okay, I'm differentiating. The moment I differentiate, I drop the dx. Okay, so this becomes 5 times 2 is 10. X to the power 2 minus 1, folks, for millions of years has been 1. Okay, so it's still 1. So that becomes 10x. The power of the x is 2 minus 1, which is still 1. Now we saw, when we did the first principles, if we have a 4x, the derivative of 4x is that which is written in front of the x. So that will be plus 4. Let's quickly remind ourselves why. The power of this x is 1. I reduce that power by 1, the power of the x becomes 0, and x to the power 0 is 1. Okay? And the derivative of my constant is 0. Okay, now you remember, before the ad break I said to you we're going to come back to that. Let's quickly see why. Why is the derivative, and I left you with d dx of the number 6. Now what did we say? We say, okay, it's 6x to the power of 0, because it's 6, the number 6. Now just look at that. If you bring the 0 down, it becomes 0 times 6, folks, and 0 times anything is always 0. It hasn't changed yet. We'll let you know when it changes, but so far for the past trillion years, 0 multiplied by something remains 0. Okay, so I hope that puts this rule for you a little bit in perspective. Let's look at some more rules that govern the way we treat our derivatives. There's 2 more rules that come up. I want to talk about this one. If I have 2 functions, f of x and g of x, I'm adding or subtracting them, and I'm taking their derivative, then it is the same as taking the separate derivatives and adding and subtracting it. Now that's exactly what I did just now with the previous question. I took 5x squared and I subtracted 4x from it. The one function was 5x squared. The second function was 4x. Okay, so now I took their derivatives separately. So an example, a quick example, another one, the d dx of, let's say, 4x to the power 3 minus 2x squared plus 4x plus 1. Okay? I want to differentiate that function. Now, there's 4 terms there. Okay? Be careful. So this is not just f of x and g of x. This is f of x minus g of x plus k of x plus p of x. I'm treating every single term as if it was a function by itself when I differentiate. And that is what the rule is saying in plain English. Okay, so I've got a cubic function to start off with. Here we go. Let's do a term by term differentiation. 4 times 3 is 12. X to the power 3 in your head. It's called mental gymnastics. You do it in your head. You do mental gymnastics. 3 minus 1 is 2. And there you differentiated the first term perfectly. Okay, so let's say you dealt with f of x. Now I move to the second term and I'm minusing g of x. The second thing is a parabola. Whoopsie. My second term is a parabola. Let me just send it back to where it came from. There we go. Okay, so I have minus 2 as my existing coefficient. I times it with that 2, I get minus 4. And the x is still there. Why is the x still there? Because the power of the x was not 1. Remember, if the power of the x is 1, the x just simply dissolves. Now, folks, let's have a look. What's the new power? Let's see. 2 minus 1, yes, for centuries, is still 1. So it stays minus 4x. And now I move to the third function, the 4x over there. Okay, now notice there's an x. There's an x. The power of the x is 1. The old power is 1. I reduce it, the power becomes 0. Therefore, the derivative of that 4x is simply just 4. And then, by the same reason that you see it happening earlier, that's a constant. And the derivatives of a constant, of any constant for that matter, is always 0. Okay, so this is what the rule does. It says, if I take the derivative of a sum of a lot of things like that, that's the derivative of a sum of things. I might as well just take the separate derivatives and add or subtract them from one another. Okay, what looks like a very complicated rule is actually very, very easy when you apply it in practice. Okay, folks, now let me go back one over here. What this rule does for us, what that rule does for us is it tells us one thing. You have to write your x as a power. Listen carefully. You have to write the x as x with a power, because the derivative operates on the power and on then obviously also on the coefficients. Okay, but I cannot have the square root of x. I must have it as x to the power of something, and I know that you know that that power is a half. And the same with something that is a fraction. If that was 1 over x, I have to write the 1 over x as something with a power. Now, we did that in our previous question. You see, there you had the 1 over x, and what did I do? I wrote it as x to the minus 1. Why did I need to do that? Because the rule tells me that I need x to the power of something, not 1 over x to the power of something, or a square root or a cube root over that x. So remember that. That's going to become important a while from now. Okay, the last rule that we have here, folks, is a rule that I often neglect to remember. I just need to get back to where I was. Oh, folks, now I need to go back. Oopsie. Okay, Kai, you look for some question for me over there while
That's what
I'm
I'll be
quickly
doing.
find my page again.
All right, so guys, I hope you guys have been following nicely. You've been learning a lot of stuff, guys. I hope you keep on posting. Still haven't seen many questions yet, but they're still coming. And I think we'll probably attack them in the last segment. How's that, Jacques?
Excellent. Let's do that.
All right.
Let's do that.
Awesome.
But
So,
folks, you've got to remember, we're going to stop talking to you if you don't talk to us. So keep those questions coming. This section in an exam is worth an enormous amount of marks. It is the section where you should get full marks for. And if you cannot differentiate in an exam situation, folks, you're going to be in serious trouble. And it's actually very easy. Okay, let's move to the last rule that I have on the screen here. Now, this rule says k multiplied by f of x, which means, remember, k is a constant. I want to differentiate with respect to x, k multiplied by the function f of x. Now, they say that's the same as removing the k and multiplying it with a derivative. Now, let's see a simple example. A simple example would be to say f of x is 6x to the power of 4. Okay, I want to differentiate that thing. Now, can you see the constant in this case is the 6? So before I differentiate it, I can say, okay, that's interesting. So I need to do what? I need to say this is 6 times the derivative d dx of x to the power of 4. Now let's see if that's true. Let's see, what is the derivative with respect to x of x to the power of 4? If I continue here, I get 6 multiplied by 4, x to the power of 3, which is, if I clean it up, 24x cubed. Now this is going this route, applying the rule, taking the constants separately, and then differentiating the x, and then multiplying the answer at the end. Look at it, that's what it says. It says take the constants separately, here, and multiply it by the derivative of whatever was left. Okay? And in this case, f of x became 6x to the x to the power of 4. But if I just apply the rule, the normal power rule for differentiation says take the coefficient multiplied with the power, you get 24. Reduce the old power by 1, and you have the new power. Okay, so folks, it's not difficult. This is what I'm saying. A quickie, then we're going to move to the next page. If I have a constant and I multiply it with a function f of x, something to this effect, 6x to the power of 4, I can keep the 6 spare, quickly differentiate x to the power of 4. X to the power of 4 differentiate is 4x cubed, and then times the 6 back in, I get 24. What it also says in the second rule is if I take the derivative of a lot of things that I'm adding or subtracting from one another, I might as well just take every single one of those derivatives separately and add them or subtract them from one another. Okay, and then the very, very last one, or the very first one we actually saw, was this thing. Folks, this is the most powerful thing. It's called the power rule for differentiation. It replaces your first principles. Okay, so you'll see in an exam, differentiate with respect to first principles questions. Those are between 5 and 6 marks. And then you will see questions that say, differentiate by using the rules of derivatives. And those are these rules. This is the rule that they want you to use, the power rule, without using your limit. Okay, Ty, have you got something for me?
Yes, we actually have one from Maladzi. He wants to find out f of x equals x minus x to the power of 3 plus 10x to the power of 2 minus 17x minus 20. Draw a sketch of f. Do you think we could draw a sketch of f, or do you think...
It's Maladzi. His name. Maladzi, listen to me, young man. you are going to do that. That is the question in calculus that's going to get you 15 to 18 marks. But that's the drawing of the function. Okay, what we're doing still, we're still trying to get into the door. We're still trying to differentiate. So I'm glad to hear you getting so excited, but that is going to be a show not so far into the future where we actually are going to draw the cubic functions. So hang in there, and please post that question again when we talk about drawing the calculus graphs.
But for now, I think we should take a little bit of a break. Huh?
I think that would be lovely.
Okay, awesome. Guys, so you know the drill. Keep posting. Keep posting. Like Jacques said, keep posting. Like Maladzi did. Keep posting. But for now, guys, we're going to see you after this break. See you soon. Welcome back, Mindsetters. Hope you've had a nice little break. You know, you had a nice little brain, like calming your brain down just a little bit. But, as I always say, you need to switch it back on again, because we need to get back into the session. And guys, this is the final leg of the show. So guys, make sure you get those questions in if you want them answered. Jacques, take it away.
Great, thanks, Ty. Folks, I'm not going to waste any more time because there's a lot I want to do with you. I'm going to do 4 derivatives. Different types of derivatives, different things for you to watch out in an exam. The first one has a fraction in it. If you look at this question, it's a polynomial on top of a polynomial. And what are they asking me? They're asking me to differentiate it. Now remember, just to remind you, and I'm going to keep on reminding you all the time, a derivative is a gradient. Okay, it's a change of y over change in x because it comes from an average gradient. So it is, find the gradient of that function. Okay, folks. Now please, the derivative is not, look at this and make a note, it is not the derivative of the top, 2x minus 5 over the derivative of the bottom. That is the classic mistake. When I see that in an exam, I want to break my false teeth. That's how angry I get if you write that. You cannot differentiate a quotient. That's something on top of something else. You need to simplify it. Why is that so? The rule says you must work with f of x being expressed as a power. Why? Because its derivative is the power multiplied by the existing coefficient, x to the n minus 1. Okay, so I need x to the power something. To get that, I need to first simplify that fraction. Okay, so I'm going to work a little bit on f of x. So please, folks, it is not the derivative of that over the derivative of the bottom. It is not that. Remember that. Okay, the F word of mathematics, fractions, fractions. You stop in your track when you see a fraction. Okay, now let's see what can we do to this. Well, one thing I can see is we can factorize the top. Now we know, because this is such a pathetic, ugly fraction, that the denominator has to cancel. So immediately my one factor I know is going to be x minus 2. Let's see what's the other one. Well, the other one has to be x minus 3. Let's check. Minus 2 minus 3 is indeed minus 5, and minus 2 times minus 3 is positive 6. And there's our problem solved. Those two things disappear. Okay? They don't form part of the problem anymore. Now I have something that I can differentiate. I have f of x, which is x minus 3. Now I can say, therefore, the first derivative with respect to x is the derivative of x, which is 1, minus the derivative of 3, which we know is naught. Why? Because the derivative of a constant is always 0. Don't forget that. Okay, folks? So please remember, if there's a fraction, you need to simplify the fraction first. How do I simplify it? I take the denominator and I divide it into the numerator. Now there's many ways to do that. In this case, my denominator was a binomial because it has two terms. To get the binomial, I need to factorize the top. I cannot just take the x and divide the x into an x at the top. I can't do that. Remember that. Okay? And I cannot say 2 goes into 6 3 times. Okay, folks? I cannot divide over those terms, those pluses and minuses. I can't. Don't do that, please. You're going to throw marks away. Okay, that's a binomial. I factorize the top. I simplify it. What it is not is this thing. The derivative is not the derivative of the top over the derivative of the bottom. And for those of you that didn't understand what I just said, I cannot say 2 goes into 6 3 times and x goes in here x times and then say, okay, that's what's left. I can't do that because there's a minus. This is a binomial. The whole thing must go into the top, not this part into that part and this part into that part. Okay, folks, so that's also something to watch out for. Let's look at the next one. Now, remember my rule. My rule says write it as a power, and it's not always going to be that my function is given in terms of x. This one is given in terms of y. It says to us that f of y is equal to the square root of y. Now that square root is not a power. It is not a power. Okay, to be able to apply my power rule, I need to say, okay, let's do a bit of work here. This is y to the power of a half. If there's nothing in front of the root sign, it's a square root. Okay? And you know from your exponential rules that the nth root of a to the m is nothing other than a to the m over n. Okay, don't forget that. You're going to need those exponential laws now because you're working with powers and stuff. Okay, folks, so the power of the y is 1. There's an invisible 2 in front of the root, so the power is a half. And now the rule. Now it's ready. Therefore, the first derivative with respect to y will be nothing other than the coefficient comes down. It multiplies with the existing coefficient, which is 1. So it's a half times 1, and that is still a half. The old power, now be careful, is a half minus 1. There's a little bit of mental gymnastics. You know that a half minus 1 is minus a half. So this becomes a half y to the power minus a half. Now, we're not messy in mathematics, are we? I don't think we are. Okay? We give them back their root. But now there's two things happening. Oh, be careful. Be very, very careful. If I clean this up, the first thing, it is a half multiplied by 1 over y to the power of positive a half. I make that negative power positive by bringing in my exponential rule. The rule says x to the power minus m is nothing other than 1 over x to the power of positive m. That's what happened there. Okay, now look at this. This leaves me with 1 over 2. Now I just saw that y to the power of a half is nothing other than the square root of y. Difficult. There's more than one thing to do here. You formed a fractional power. You differentiated it, and the power became negative. And if the question says, leave your answer with positive powers, folks, then you've got to go back and make that negative power positive. And it becomes positive by reciprocating it. And when we were very, very nice, we showed them, you know what, we know the power of a half is a root. So the derivative of the square root of y is 1 over twice the root of y. Okay, watch out for that. Remember to write it as a power. Okay, let's look at number 3. Number 3 has got something different happening. Look at that. We have a product. Z minus 1 times Z plus 1. Now we all know. Okay? Please, 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 folks. Like the previous one where I said the derivative of something over something else is not the derivative of the top divided by the derivative of the bottom. The same here. If I say to you x squared plus 1 and you have x squared minus 4 in this case, then you cannot say that the derivative is the derivative of this bracket multiplied by the derivative of the second bracket. It is incorrect. You first need to multiply before you differentiate. Like in the previous one, you first needed to divide before you differentiate. One day when you go to university, it's not always so easy to divide. Then you're going to learn different rules that will help you deal with those. But you're at school, so you first divide, you first multiply. Always say that to yourself. Okay, so I've got a bit of work to do here. I've got to fix it up so I can differentiate. Now check my variable this time around is z. Okay? If I multiply that out, just get rid of that line. If I multiply that out, I get z squared minus 1. It's the difference of squares. Okay? Therefore, my derivative with respect to z will be, now let's see, term by term differentiation. The derivative of z squared is twice z to the power of 1, and the derivative of the constant minus 1 is 0. So my derivative is done. I want to show you if the notation was different quickly. Let's just say I had y, which was equal to z squared minus 1. Now I want to differentiate it. So what do? I then write d dz of y. Why am I saying that? Why isn't it d dx anymore, folks? Because my variable is z. Okay, so it's the same as d dz of z squared minus 1. Now check the beauty here again. What happens? I'm now going to differentiate. So now I drop my d dz, and my answer is 2z. With this one, the moment I differentiate, I indicate I'm differentiating by saying f prime z. When I use the d dz notation, how do I indicate I'm differentiating? By dropping the d dz. Okay, the derivative with respect to z. And as promised, my fourth question, I'm not going to get to the fifth one. Look at this one now. It's a different fraction. It is still a fraction. Okay? This time around, look at what's different. I've got one x in the denominator. I don't have a binomial. I have a x. So that x must divide into each of the top. Let's have a look. To fix it, y will be x cubed over x plus twice. Now remember, we said I don't want roots. I want powers over x minus 3 over x. It's still not ready because there are x's in the denominator. Okay? I've just got the x's out of the roots and stuff. I'm dividing every term by the x, and now I prepare it. Still preparing, so it's still y. X squared over x, or x cubed over x is x squared, plus 2, x a half minus 1 is minus a half at the top. And here, I've got 3 over x, and we know that that is minus 3x to the minus 1, folks. Now you can see, every term has got an x with a power. Okay, and James is whispering in my ear, I've got to hurry up. dy dx. I'm now going to differentiate with respect to x. Okay, what is that? 2x. Over here, the minus a half comes down, makes this minus x to the power minus 1.5. It's minus a half minus another 1. And over here, the double negative makes it +3, and the power reduces by 1. So that power becomes -2. Okay, folks, all you need to do is wrap it up, make the negative powers positive, give them back their roots, and you have your answer. But in 90% of the cases, you will get full marks for that. Okay, I hope that helped you, folks, and good luck with your calculus. Ty, over to you.
Guys, hope you had fun. You know the drill. Get on the page, get chatting, talk to each other. Guys, I cannot say this enough. And guys, I will be finding those people who won these calculators for the best post this week. But for now, guys, I'm just going to say me and Jacques had fun. And from everyone in the crew in the studio, we're going to say peace out and see you next time. Bye.